we did was, so we went over some of the circuits. So we looked at the full wave rectifier as a circuit, and then we went through the full wave uncontrolled rectifier waveforms. Any issues with those? Everybody's fine with those? And then we did the center tapped rectifier. The output waveforms are identical, except the only difference is really the peak voltage or the diode voltage, right? The peak voltage on the diode, yeah. So we realized that in this case it was double the voltage rating of the previous case. And then we did the RL load case. We looked at the output voltage, output current, diode currents, and then we also looked at the supply current. And then, for a large inductance, fine, you keep increasing the inductance on this RL circuit, in this RL circuit case, and what happens is that the current becomes flat. So, big inductance means little to no change, in current. If I say theoretically infinite inductance, meaning current will never change. So fine, instead of having this current going up and down, it's just a flat positive, flat negative waveform. It's not realistic. This is not a realistic circuit. This does not happen in reality. It's just, it's an approximation that we use, for example, to be able to calculate losses, RMS values in a simple way, right? Here the current waveform is very difficult to. You cannot come up with an equation for the current waveform. So we said we're gonna have to resort to the Fourier series of the voltage. From the Fourier series of the voltage, calculate the Fourier harmonics of the current, right? And then from there we can do whatever calculations we want, right? But if I can approximate, if I can say, okay, the inductance is big, so the current is just flat, then the equation for a flat value is just a number, right? So in that case, you can easily find areas under this rectangle or RMS values or peak values, stuff like that. Just to simplify matters and get you to understand how the circuit functions. Yeah. So we went through that. Supply current in this case, of course, is just a square wave. The RL source, we did that for the case of low DC voltage and or large inductor case. So we said the low DC voltage case with a reasonably large inductance case, and then we did the case where we increased the DC voltage or we maintained the DC voltage and decreased the inductance, for example. So we talked about the continuous and discontinuous case here as well. From a waveform perspective, we did not touch equation. Then we stopped. I think we did not cover the output capacitance filter, which will help, which is going to be a review for the quiz anyway, right? So the quiz that you did was a half-wave rectifier with a capacitive output filter. So we'll do this. We'll do this again so that maybe it helps. Maybe in the next exam you get it. I don't know. So it's so let's see the capacitive output hint. Maybe I don't know. But it's important. It's important to understand this waveform, right? So let's go over what we had here, what we're looking at here again. So what we have is the full wave rectifier, and let's see. Looking at the full wave rectifier circuit, this is my source. We'll first do it without the capacitor, so just the resistive case, and then we'll see how things change when we add the capacitor. One, two, three, four. Okay, so this is my 1.5 cycles of my input voltage, not one. Okay, so this is V input plus minus V output. So V output looks like, again, in the positive half cycle, diodes 1 and 2 will conduct, right? And in the negative half cycle, diodes 3 and 4 will pick up the voltage, right? They will automatically, they will act like the freewheeling diode in the half wave rectifier case. So as soon as the voltage goes negative, they will pick up the load. Okay? And in all cases, current does not change polarity. Current is always flowing out this way. out this way into the load, right? So the polarity of the output voltage will not change, right? So if we draw the output voltage in this case, that's this blue waveform. Has a peak value of Vmax. Okay, peak value of Vmax. So this is V output. So I output in this case looks exactly the same as V output, right? It's just scaled by the value of the resistor. That's fine. So how about I source? So let's draw I output. Just make it easy first. Okay. So I output looks exactly the same as this, right? So if I output looks the same, so this is I output. Okay, so this is I output. Looks exactly the same as V output, except its peak value is Vm over R. In this case, that's fine. So what does the source current look like? Again, let's do Kirchhoff current law at this node. Okay, so at this node, I have source current coming into the node. This is I supply or I source, and I have diode 1 current here, and diode 4 current here, right? ID4 coming in to this node, and the IS coming into the node, and ID1 coming out of the node, right? So ID1 is coming out, ID4 is coming into the node, IS is coming into the node, right? So I have IS plus ID4 is equal to ID1, right? Or IS is equal to ID1 minus ID4. ID1 minus ID4. So for me to find IS, I need to find ID1 and ID4. I know that in my first half cycle, diode 1 and diode 2 are conducting. In the second half cycle, diode 3 and diode 4 are conducting. And then we go back to diode 1, diode 2, right? So I want to know what, if this is my I output, then I output is actually being carried by D1 and D2 in this half cycle. How about what's the value of ID1? So ID1 and ID2 are equal to I output in the first half cycle. Okay? ID1. So ID1, I will draw it in blue, okay? Because I need ID1 and ID4. So ID1 is equal to what? Yeah, in the first half cycle, ID1 is equal to I output, right? Because in the first half cycle, ID1 is conducting. So ID1 in the first half cycle, ID1 is equal to I output. So it looks like this. This is I output, right? How about in the second half cycle? What does ID1 look like? 0, 0. And then it repeats again in the next half cycle, right? So this is ID1. And then let me draw ID4 in red. So ID4 in red. So what is ID4 in the first half cycle? 0. And then it looks like the output current in the next half cycle. This is ID4. ID3 and ID4 are the same, right? It's the same current. ID1 and ID2 are the same, and then ID3 and ID4 are the same. Okay, so this is the red is ID4, the blue is ID1 on this curve. Okay, so now I want to draw IS, which is ID1 minus ID4. So ID1 is the blue, ID4 is 0 here, so it's this waveform, right? The blue waveform minus 0. It's this blue waveform. And then it's the blue waveform, which is 0 minus ID4. So it's this, right? So my input, my supply current is a nice, or my source current is a nice sine wave in this case. Everybody's happy with this? Okay, so now, what were we doing here? What was, the capacitor, sorry. So this is without the capacitor. So now let's do the case with the capacitor. So now Why do we need to put this capacitor? Because if I look at my output voltage, it varies between V maximum and 0. So my delta V, which is my ripple voltage in this case, is V maximum, is equal to my maximum peak voltage. So if this is 10 volts, what is my ripple? 10 volts, right? So if I ask you in the quiz for ripple to be maintained within 5% of ripple to equal 5% of your peak value, right? If the peak value is 10, what is the new delta V that you want? This is the current delta V. I want to put the capacitor because I know what the capacitor will do is it will charge from the supply, and if I've properly chosen my bucket or capacitor size, then it will maintain the level even though the supply is not feeding it, and it will maintain continuous current to the load, right? So it will maintain its level if I properly chose, right? Remember that level analogy, level of water, bucket and load and stuff like that? So if I properly chose my size of capacitor, then the level, which is analogous to the voltage, will be maintained almost the same. It will change a little bit, but it will change 5% only with respect to the peak input voltage, and I will still be able to always feed my load, right? So that's the objective. I want to find the new delta V. The new delta V in the quiz I gave you was, the new delta V is 5% of the input voltage, of the peak input voltage. So if the peak input voltage was 10, then 5% of that is half, right? So instead of delta V being the full 10 volts, in this case it's the full 10 volts, right? Now the delta V, I want it to be half a volt, right? So I want this new delta V. I'm looking for this new delta V. So this delta V prime. I want a delta V prime that is only 5% less than my peak value. So it's half a volt less for the case of 10 volts, for example, or it's equal to 0.95 of the peak volt. So if you go from Vmax, you write 0.95 Vmax, and you go down a little by 5%, and it means that you have a capacitor that is allowing your output voltage to look like what? Like this, right? Is everybody okay with that? Right. So now, how is the circuit operating? If I put this capacitor in there, initially what's happening? The capacitor is not charged, correct? For example, assuming the capacitor is not charged initially, then the capacitor voltage. I'm drawing the capacitor voltage or the output voltage because they're the same, right? The capacitor voltage and the output voltage are parallel, right? So initially the capacitor voltage is 0, so the output voltage is 0. Then my input rises, so my diode 1 conducts, diode 2 conducts. So I'm putting my supply voltage across my capacitor and resistor, right? So in the first half cycle, the source is supplying the capacitor and supplying the resistor. Okay, so it's supplying the capacitor and the resistor, right? They're both across the source supply. The equivalent circuit looks like this: just an AC source with a capacitor and resistor across. Right? Both of them will be fed from the source. Right? And then this happens all the way until maximum voltage here. So at maximum voltage, my capacitor has maximum voltage across it. Sure, great. And then what happens? My supply voltage, which is the blue, starts to go down. Right? It's starting to go down after it reaches its maximum value. It starts to go down. I have chosen a capacitor value to be large enough so that when I draw current, when my load is connected, actually let's do the case without the load connected. If the load is not connected, so there's no resistor here, what will happen? The capacitor will charge, the source will charge my capacitor. At some point, the capacitor voltage will reach the maximum supply voltage. Beyond that point, the supply voltage starts falling, right beyond that point. If the supply voltage starts falling and the capacitor voltage is maintained because I don't have a resistor, in this case, what will happen? This capacitor voltage will be higher than the supply voltage, so diode 1 and diode 2 will stop conducting. Right? I mean, this is source. Remember the source, the RL source circuits? If I had increased the source, what would have happened? We started conducting only after the AC source was greater than the DC source, right? So it's the same thing here. Here now the DC source, which is the capacitor in this case that I've charged, is higher than the input source. So the diodes will stop conducting. Diode 1 and 2 will stop conducting. Right? So they will not conduct. So they will conduct all the way from here until the maximum. Conduct means what? It means current is coming from my source. I have current coming from my supply. And current coming from the supply, if the supply is a sinusoid, remember, capacitors and inductors, what would they do? They shift by 90 degrees, right? So if I'm applying a sine wave of voltage by 90 degrees, IC equals C dVc by dt. It's the integration of differentiation of voltage. So you shift the voltage by 90 degrees. You will lead the current in the capacitor will lead the voltage by 90 degrees. Right? So in that case, what will the supply current look like? Exactly. So it's like a cosine that starts here. And then where will it stop? In this case, with only the resistor, with no resistor there, it will just stop exactly at pi over 2. Right? So do we agree? This would be supply current in this case. Now I have a resistor. Okay, if I put the resistor in there, and then so after that, what's going to happen? Sorry, assuming still no resistor, this would be my supply current. It has charged my capacitor to Vmax. The capacitor voltage will be maintained at Vmax because it's an ideal capacitor, right? No resistance at all. It will be maintained at Vmax. It will never go down. If it never goes down, then the supply will never conduct again. Never conducts again because always the capacitor voltage is either equal to or greater than the supply voltage. Equal to or greater. So no current will ever flow from the source to the capacitor again. So that would be the end of it. If this would be the supply current if I didn't have a resistor connected, right? But of course that's not the case. So that's not the real case, right? So the real case, we will have a resistor connected. So if the resistor is connected, what's going to happen? At this point here, we said the supply voltage starts falling. That's fine. And the capacitor voltage will also start falling. Because of what? Because as soon as you've charged the capacitor to its peak value, this capacitor has a large voltage across it. And this capacitor also has a resistor parallel to it, right? So this capacitor will tend to want to feed the resistor, right? So at some point, so what's going to happen is there will be a point where the supply voltage and the capacitor voltage are equal, right? They're equal. They are both equal. So if they are both equal and they have a resistor connected across them, they will feed this V maximum voltage will be feeding the resistive load. And then at some point, the supply voltage starts falling faster than the capacitor voltage. They're both going to feed now this resistor. And then at some point, the supply voltage is falling a lot faster than the capacitor voltage because I've properly chosen sides of the capacitor. If I've chosen a very, very small capacitor, then it's this point where they will deviate. Let's say in this case, the book calls it theta, an angle theta. So that it's at point theta here, I think, yeah. So they call it some angle theta. At some angle theta, the supply voltage and the capacitor voltage will deviate because the supply voltage falls a lot faster than the capacitor voltage because I've properly chosen my size of the capacitor, right? So what's going to happen at this point? At this point, the capacitor voltage is higher than the supply. So diode 1 and diode 2 will stop conducting. They were conducting all the way until this point, actually. When I put the resistor, when I did not have the resistor, they were conducting only until the peak, right? Only until the peak. And then when I removed my resistor, the diode, the current had to conduct a little bit more to a point, some point theta. Okay, some point theta, a little bit after the peak value. So this point is a little bit, just a small portion after the peak value. Where does this point occur? The way that the book calculates this value of theta is they calculate the slope of the input voltage and the slope of this exponential equation. Again, this is an exponential equation because it's an RC circuit. As soon as the two diodes disconnect, right? Then what does my circuit look like? The circuit looks like this. Just the capacitor and the resistor. Right? As soon as diode 1 and 2 disconnect. Diode 3 and 4 will not connect because we're not in a negative half cycle. So diode 1 and 2 were conducting, and then they stopped conducting. If they stop conducting, they disconnect my RC circuit from my input source. They disconnect it from the source. Right? So if I disconnect it from my source, then I'm not taking any current from my source anymore. Right? So my circuit will look like this RC circuit. It has you can solve for current, first order differential equation. The solution for the current is AE to the minus T over tau, so it's an exponential equation. So we have the equation for expression for this exponential here until a certain point. A certain point where what happens? Where the supply voltage now is higher than the capacitor voltage. If the supply voltage becomes higher than the capacitor voltage, then diodes 3 and 4, again, will start conducting in the second half cycle. And we repeat the cycle. Is it okay? So now what's happening? Let's look at this point. And here until here. So here we said I was charging my capacitor. Right? And then what? So I charge my capacitor, and then I stop charging my capacitor. And I've disconnected diode 1 and 2, have disconnected my RC circuit from the source. So my supply current will stop. It charges the capacitor and that's it. And then what happens? It's zero. I've disconnected diode 1 and 2 are disconnecting the RC circuit from the supply. So it's zero. And then what happens? At this point, diodes 3 and 4 start conducting again. Diodes 3 and 4 will conduct. Right? So if diodes 3 and 4 conduct, I'm connecting this circuit again. But I flipped the terminals of the supply because now I have, this was originally my terminal 1 and terminal 2. I was originally taking terminal 1 and putting it at the top here. Right? And then terminal 2, I was putting it here. Right? But now in the second half cycle, I'm taking terminal 2 or terminal, let's say 2 prime, right? I'm taking terminal 2 here and sticking it up there, which is 2 prime here, and then taking 1 prime, and I'm putting it down here because diode 4 is conducting, right? So I flipped the source. I have the same circuit, but just the polarity of the current now is flipped. So what will it look like? As soon as the capacitor voltage is less than the supply voltage, the supply will try to charge the capacitor, right? As soon as I try to connect the supply across the capacitor, the supply will try to charge the capacitor, right? And it will try to push the capacitor voltage to be equal to the supply voltage. And current through a capacitor can change abruptly, right? The current IC equals C dVc by dt. Voltage, what's the equation for voltage across the capacitor? The equation for voltage across the capacitor, I would, Vc is equal to, I bring the dt on one side, divide by C, and then integrate the current. right? So voltage across the capacitor has to build up. You integrate voltage. I mean, you integrate the current to calculate the voltage across the capacitor. So capacitor voltage cannot change abruptly. It cannot. But capacitor current can change abruptly. Because what happened here? What happened was I want to change, so the capacitor voltage was a certain value, right? I want to abruptly change it to equal supply voltage. So there was a certain dV by dt. There's a, capacitor voltage was, it was falling like this, right? It was falling like this on this line, and now it needs to completely change its slope, right? So this was my slope for the capacitor voltage, and now this is my new slope for the capacitor voltage. Is this a significant change in slope or not? It's not a gradual change, right? Slope changes gradually is like this. But now I went from a negative slope all the way to a positive slope. I changed my slope drastically. So if I change my slope drastically, I expect to see a big jump in current, right? I mean, this is, big change in V, right? Big change in V, significant change in V quickly in a very short period of time. So I expect to see a jump in current. So what happens will be, what we'll see is this. A jump in current to the negative side, and then you're charging your capacitor. You're charging your capacitor. Until this moment, you're charging your capacitor. And then what's going to happen? If the capacitor voltage looks like this, what will happen again is, capacitor voltage now, in this case, beyond this point theta, which is close to the peak, okay? Capacitor voltage is higher than the source voltage, so you disconnect again. So diodes 3 and 4 are disconnected. So if you disconnect diodes 3 and 4, and diodes 1 and 2 are not going to conduct because we're not in the first half cycle here, we're in the second half cycle where D3 and D4 would have conducted, right? So since this is the case, then the current goes to 0. Because you've completely finished, you charge your capacitor. After you charge your capacitor, the current is 0. It's 0 until when? Until you're going to charge your capacitor again. What's happening here? Same thing. I have a significant change in the slope of voltage, right? So I will have a jump in current. So current jumps up here, and then does this. Because then the slope is smoother, right? Here there was a big slope, right? Big change in slope. Here the slope changes gradually, all the way until 0, right? So if the slope changes to 0, then IC becomes 0. Right? So this is my, this is what we're doing. This is the supply current will look something like that. No, a huge ripple. I mean, the current has ripple, but my voltage doesn't have, my voltage now has a bit, where's my ripple voltage now? This new, smaller ripple, right? Before it was from peak all the way to 0. Now it's from peak to somewhere 5% less than the peak, right? Or 10% less than the peak. It's a design criteria, whatever you want, right? Some design criteria. So this would be my supply current. How about capacitor current? Very similar. What? Slope of V out. Yeah. Yes. So if the slope of V out, that's a good point. So if I want to draw a capacitor current here, it's capacitor current. So my supply is doing what? My supply is charging my capacitor as well as feeding my resistor, right? So a small amount of it is feeding my resistor when I'm charging my capacitor, right? So maybe a small amount less a small amount of this is going to what? A small amount of this is going to what? To this part is going to my load, right? Because if 1 and 2 are connected, the supply is connected to my capacitor and my resistor, right? So a small amount of the current is going to my resistor, a larger amount is going to my capacitor, right? So let's say this is my capacitor current. This let me draw it in a different color. I'll draw capacitor current here, right? Same thing here. You agree? You agree? Same thing here. So this black is, places where we know capacitor current, what it looks like. But is this it? Capacitor current, remember when the supply is connected through diodes to the output, I'm charging my capacitor and feeding my load. And I explained that here. Everybody's happy with the black waveform? Okay. But now, is my load current continuous or not? Let's draw load current. Okay, so we didn't draw load current after putting the capacitor, right? We drew the output current here, which is the load current, before the capacitor. What does the load current after putting the capacitor look like? Like this, and then exactly like the voltage, right? Because it's a resistive load, exactly like the voltage. So it will look like this, correct? So we'll have the ripple as well. So until here we explained it. So now what's happening? There is load current, right? Where is this current coming from? Exactly, from the capacitor, right? So that means that I have still something missing in the capacitor waveform. It cannot be zero, like the supply current, right? Cannot be zero. So what does the capacitor current waveform look like? The capacitor was initially being charged, right? And now it is actually feeding the resistive load. So initially the capacitor was being charged here. And then the capacitor current is flipping direction to feed the resistive load. Right? So it was initially being charged, and then it's flipping direction to supply this. Sorry. Positive. Yeah. I got confused. Sorry. I got confused. So the capacitor current. One thing to note. One wrong thing we did. We did something wrong here. So who can tell me? Not this one, and not this one. What's wrong with this? The red is fine. The black is wrong. The black on this one only, not on these two. When the capacitor is being charged, the polarity of the current is not changed. It's always into the capacitor, right? My supply current had to flip because diodes 3 and 4 were now conducting to charge the capacitor. So this black has to be on top. We agree? Right? That this was wrong. This black was wrong. This black has to be flipped because capacitor current is the same direction. When it's being charged, it's always into the capacitor, into the capacitor, into the capacitor, right? So into the capacitor, into the capacitor. That's why this is fine. This is fine. This is fine. I messed up on this one because I drew it on the supply current, yeah, right? So now what? So now this current now that is going to the resistor is being provided by the capacitor. So I see the same current waveform here is exponential. I see the exponential here. And then it ceases to flow from the capacitor. It comes from my source. Okay, now who's confused? Everybody? No, I mean it's okay. Do you see the red? Do you understand the red waveform? So the red. When does the red occur? The red waveforms occur when the diodes are connecting the supply to the RC circuit. Do we agree that I mean, if the diodes are connecting the supply to the RC circuit, then I'm charging my capacitor, right? If the diodes are connecting the supply to the RC circuit, the equivalent circuit looks like this: a source with an RC circuit across it. If I have a source with an RC circuit across it, then what I will do is charge the capacitor. Right? I'm charging the capacitor. So I'm taking supply current to charge the capacitor. So I have to, so during this period where I'm charging the capacitor, supply current will come and charge my capacitor. Go through my supply, come from my supply, charge my capacitor. So my red waveform is like this. And then from this point theta, which is close to the maximum value, all the way until the intersection of the exponential, which is the capacitor voltage, with the input voltage again, my supply voltage is disconnected. My source is disconnected from my RC circuit. So I have a RC circuit that's standing alone. This RC circuit that's standing alone is not drawing any current from the supply. So the supply current, which is the red waveform, is 0 during this interval. Right? And then what happens? Then diodes 3 and 4 are now connecting my source to my RC circuit, not diodes 1 and 2. Diodes 3 and 4. So what's the difference between the diodes 3 and 4 and 1 and 2? They just flip the terminals of my supply. So I flip the terminals of my supply and I've still charged my capacitor. I had a big jump because I have a significant change in slope, right? Big jump in current, and then the slope of the voltage across the capacitor decreases until I've charged my capacitor. So I go all the way down to 0, the red waveform. And then I repeat it again the next positive half cycle. That's the red waveform. And then the black waveform is the capacitor current. So the capacitor current, okay, when the red waveform is coming from the supply, when I'm connecting my source to my RC circuit here, my source is feeding my capacitor, charging it, and that's the bulk of what's happening. It is also feeding current to my resistive load. So a small amount of this red waveform is going to go to my resistive load, right? So that's why I decreased this by a small amount. And then the rest is being picked up, and then the rest is used for charging the capacitor. So we reduced this a little bit, and then we drew some waveform here. And then we said that what's happening here, beyond this point, which is close to, I drew it equal to pi over 2, just for simplicity here. So beyond this point, the capacitor is feeding the resistor. It's not the source, right? The capacitor is feeding the resistor in this case. And it's flipping its polarity. Because it was initially being charged, current was going into the capacitor. Now it's being discharged, current is going out of the capacitor. So I flipped the polarity, and I just drew this exponential waveform down here. And then I repeat. Okay? If you go simulate it, draw it again and stuff, hopefully you'll. Yes.
What can you say about the areas of the IC, the area under the graphs, or the negative part and the positive part?
Area under the okay, yes, good point. If you keep pushing current into a capacitor, what happens? If I push current into a capacitor here, like here, what will happen to the capacitor voltage? If I'm pushing positive current, this red. Let's say this red is the current we're putting into the capacitor, right? This is current that's going into the capacitor. So this is going into the capacitor. What is it doing to it? Look at the equation. If I'm putting this current into the capacitor, if I integrate this current, what do I get? I get a small area that's increasing, right? An area that's, something that's increasing. An integration of current is charge. Yes, so I'm charging the capacitor. So I'm charging the capacitor. If I charge the capacitor, what's going to happen to the voltage? If I integrate, and this is something this integration is giving me a value that's increasing. Right? What's going to happen to the voltage of the capacitor? It will increase. Right? So capacitor voltage will, and that's what we see here. Capacitor voltage is increasing because it's equal to the output voltage in this case. Here, capacitor voltage is increasing. Right? Every time I'm putting current into the capacitor, positive current into the capacitor voltage is increasing. What happens when the resistive load is drawing negative current out of the capacitor in this area? Capacitor voltage is what? Here, in this area. It's what? Decreasing or increasing? Decreasing. So if I draw current out of the capacitor, or I draw a negative charge out of the capacitor, or I'm discharging my capacitor, then what I have is I am decreasing the voltage. If I put positive current into the capacitor, I'm charging the capacitor, right? So do I want, what's my objective? What was the objective of my capacitor? Why did I even use it? To decrease voltage input, so to maintain voltage within a certain window, right? So that was my objective. So that means if I want to maintain voltage within a certain steady state window, I always want to be able to charge and discharge my capacitor with the same amount of charge. So if I put some positive charge into the capacitor, I remove some negative charge out of it. If I put some positive charge into the capacitor, I remove some charge out of it in the negative half cycle. So these two areas, the areas under the curve for the current, for the capacitor current, under the black curve, so this is A1 has to equal A2 in steady state. And initially, forget about this. Initially, I drew this a little bit bigger than these. I do this first black one. I drew it a bit bigger than the other two black ones because initially the capacitor was not charged. But in steady state, these black waveforms will all have the same height and they will have the same areas underneath them, right? So A1, the area under the curve for a capacitor, A1, A2, A3, A4, all of these areas have to be equal in steady state. Okay, so forget about the initial transient, but steady state, they all have to be equal. Good point. Which means I can do something very nice now. Okay, so let's say I give you a current waveform through a capacitor. Okay, so let's say I will remove this. So first, everybody okay with what's happening here? We understand what the capacitor did, the capacitor current, supply current, blah, 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 output current, output voltage, all that stuff? Okay, so that's fine. So now, let's say now I do something. I give you this capacitor current waveform. It just happens to be now equal to what we just saw, fine. But this is a capacitor current waveform. This is some IC waveform. If I give you this IC waveform, and I tell you I would like this capacitor to maintain ripple within, I don't know, 5 volts. So in some circuit, what is the value of capacitance that would do that? And I give you all these values. Let's say this is 1 amp, and this is a difficult waveform, but let's say I give you something that looks easier, okay? Let's say I give you a square wave. Right? These areas are equal, right? Well, these areas are equal, and this is IC. So if this is IC, if this is your IC, and this is, for example, 1 amp here, and this is 1 second, this is 2 seconds, 3 seconds, etc. So if this is 1 second, 2 seconds, 3 seconds, this is 1 amp, and I want delta V to be in this circuit. Again, capacitors, all they do in any circuit is maintain ripple voltage. In inductors, all they do in any circuit is maintain ripple current by storing the energy in the reactive elements. In any circuit, okay? Forget about any circuit. That's their function. You put in a capacitor, it's because you want to store. Filter is exactly the same. Filters function the same way. You're storing the energy. So the high frequency energy is being, if you're only storing if you're creating a low pass filter, you would like only the low frequencies to pass through and damp, and all the high frequencies to be attenuated from the output. So what's happening? You are storing some of the energy in some of the energy of the output, some of the energy in the low frequency, taking it to the output, and all the high frequency energy is being shorted out to the supply. So capacitors and inductors. Capacitors will maintain ripple voltage. Inductors to maintain ripple current. So my argument now is if I give you a capacitor current waveform like this, or like this, and I tell you I want to maintain delta V within a certain spec, or I give you C and tell you what the delta V is, you should be able to do it. from the equation of the capacitor. So IC is equal to C dVc by dt, right? VC is equal to 1 over C integration of IC dt, right? So this is, we said, is charge, right? The integration of current, integration of the area, or the area of area under the current curve is charge. So this is some delta Q that I've put into my capacitor. And this is some delta Q that I've taken out. And I've maintained the fact that they're both equal, so that in steady state my capacitor voltage doesn't change. So if I have now my delta Q, I've put in a certain amount of charge, I can easily calculate the amount of delta V that this delta Q will cause. Or if I have my delta V as a spec, and I have my delta Q, so my delta Q in this case is what? Area under, this is the area of this square is 1 amp times 1 second. So it's 1 coulomb, right? The delta Q is 1 coulomb. And delta V is 5 volts. So what is my capacitance? Delta Q over delta V. Of course, this is a huge number, right? Of course, it makes sense because this is 1 second. I made this 1 second. But if you make this 1 microsecond, then the capacitor size will decrease considerably and maintain the same ripple, right? If this delta, if I make this 1 microsecond, then the delta Q will be decreased considerably, right? Right, the area will be decreased considerably. So if delta Q decreases considerably, I can considerably decrease C, right? So that's where reactive elements, if you increase the switching frequency of your power supply, I can use smaller reactive elements, right? And it's the same with the inductance. I can go through and do the same thing with the inductor. I will do that actually quickly just to confirm. But with the capacitor, I'm just showing you that if I do this, any difference between this and this? Nothing. At the end of the day, this is capacitor current, this is a capacitor current. Can you calculate now the corresponding delta V if I give you a capacitance of 1 microfarad for this current waveform? Assuming you know its waveform and you can write the equations and calculate the areas, you can, right? Very simple, very simple. Yeah. So, and it's a very nice tool because now you get an intuition. Okay, same thing for the inductor. Let's do the inductor, but instead of capacitor current, we use inductor voltage, right? Because inductor equation VL is equal to L di by dt. So IL is equal to what? Integral 1 over L integral of V dt. What is the integration of voltage? Remember, think of the capacitor. The capacitor is being charged. You are adding charge to it. So it's storing the energy by charging the plates. How does the inductor store the energy? Where is the energy in the inductor stored? Not in the coils. In the magnetic field. So you build up the magnetic field, right? You're building up you can do work with the magnetic field. So that's the energy. I cannot do work with the current that's flowing in the coils. That's just used to set up the magnetic field, which I can use to do work. I can pull a motor's rotor. I can push magnet. I can make it an electromagnet. I can do stuff with it, right? So that's where the energy is being stored. And that's exactly the same thing. So the integration of voltage in this case is actually the flux linkage. That's the flux that's linking the coils. So that's my delta lambda. Instead of delta Q, I say delta lambda. It's the energy, where the energy is being stored, how the energy is being stored. And then this is my delta I. So we said that the function of an inductor is always to maintain a certain ripple current. So if I give you voltage across an inductor looking like this, I'll give you same, because again, I cannot keep increasing. If I keep building up the magnetic field or adding more current to increase the flux, what happens to the core that I'm winding the wires on? It will saturate, right? I mean, even air saturates. It has a certain amount of flux density, or a core of a magnetic material will have a certain amount of flux lines that can go through it. Beyond that, you're pushing more current into the windings, but your core is saturated. Remember the BH curve? You've reached the saturation point. So H is proportional to I, right? H is equal to Ni, right? The magnetomotive force is equal to basically the current proportional to the current that you're putting through. So if you keep increasing H, which is keep increasing I, but you're not getting any more magnetic flux. You're not able to, because the core is saturated. So it's like what? You push current, you're burning current. You're putting current and you're putting it through the resistor, through the windings, and you're just burning I squared R, I squared R, I squared R for no reason. You're not getting any additional magnetic field that you can use to do work. Right? So that's why you stop. I don't need to. I should operate in a place where any increase in current is giving me a good increase in magnetic field. So I can use it to do work. Right? But if I am just pushing current and burning losses, then it's useless. Right? So if I keep increasing current through an inductor, I will saturate the core. Right? So at some point, I have a limit on how much flux linkage I can have. Right? So it's a property of the inductor itself. Right? I cannot keep integrating the voltage. If I keep integrating the voltage, I keep storing energy. That's not possible because I have a limit. It's going to saturate. I cannot push more flux lines. Capacitor, same thing. I cannot keep adding charge because the voltage will keep rising and it will break the dielectric strength of the capacitor. Same thing, but analogy for current is, in the inductor case, it's a voltage, right? So here I cannot keep adding current because the voltage will rise for a capacitor. Here I cannot keep adding or keep increasing voltage because the magnetic flux lines will saturate the core and I will just be burning power loss, right? So I end up with a similar equation, but instead of V and C and charge, I have flux linkage, current, and inductance. So same thing. If I give you this, if I tell you this is inductor voltage, area under it is this delta lambda. And then I'm telling you I want to maintain ripple current to within 5% of the load current. Whatever load current is 10 amps. So I want to maintain ripple current to be within half an amp. Right? So how do you do that? So I have half an amp, delta I is equal to half an amp. Let's say assume this is 10 volts, for example, and this is 1 second still, okay? So this is 10 volts, this is 1 second, and the area here is 10 volt seconds, right? So this is delta lambda is also 10 volt seconds, right? So L is equal to what? Delta lambda is 10 over 0.5 equals to 20 Henry. Of course, this is crazy. It's a huge inductor, right? Also because I did this. I used 1 second, right? 1 second, I mean, our fundamental cycle, our 50 hertz cycle is 20 milliseconds, right? So, I mean, this would have been 10 milliseconds in the case of a 50 hertz situation where, let's say you're building an inverter, a power electronics inverter that is interfacing your solar energy to the grid. I need to put an inductor between my power electronics inverter and the grid. This inductor, what does it do? It maintains ripple current so that you push clean current into the grid, not something with high THD. So you need to design an inductor for that case. How do you design an inductor for that case? Look at the inductor voltage. This is the voltage across the inductor, right? What does then, because you know the voltage because you're designing a power electronics converter. Your power electronics converter is connecting switches and putting voltage across the inductor, positive, negative. So you can draw the waveform of voltage across the inductor. And then if you have the voltage waveform across the inductor and you know how it looks like and how much time, etc., then you can easily calculate this area under this, and then calculate how much inductance you would need to maintain ripple current to be within a minimum certain value. Here, for me to maintain ripple current within half an amp, I need this inductance for this situation. If this 1 second is shrunk to 1 microsecond, what's going to happen? This delta lambda will decrease a lot. If it decreases a lot, then it decreases my requirements for inductance. Hence the effect of frequency on the reactive elements again. So we did it for the capacitor and the same thing for the inductor. So high frequency power converters, if I want to deliver 1 kilowatt using these simple rectifier circuits that we're talking about, the AC-DC converters that we're talking about, are very simple rectifier circuits. These are operating at what? 50 or 60 hertz, right? The waveforms that we see here are what? This is at what? This is here, up to here, is assuming 50 hertz input. This waveform is now at 100 hertz, right? It's double the input frequency. Right? So this thing is operating at 100 hertz. So I need a certain capacitor, right? But if I make this thing happen at 100 kilohertz, right? Then what happens to the capacitor size? We just said it, guys. What's going to happen to the capacitor or inductor size if this 1 second becomes 1 microsecond? This area, the delta lambda, will become small. L is equal to delta lambda over delta I. So delta lambda will become small, meaning L will become small. C was the same thing, delta Q over delta V. If delta Q becomes small, which is the area under the current through the capacitor, if that becomes small, then the capacitor becomes small. And that's why people, it's the area of research now that's interesting, at least from my perspective. And it's actually not a lot of power electronics only. It has a lot of, device modeling electromagnetics, is high frequency power conversion. Because now you can make things so small. Like there's one guy, a professor at MIT, he's like making a 1 kilowatt power converter like as big as a credit card. Literally like a credit card, a 1 kilowatt power converter. Which is, I think the power supplies on your PCs are like 500 watts or 400 watts. Right? If you've bought, if you assembled a PC, bought this, bought that, you'll go buy a 400 watt, 500 watt, and then for these crazy new Alienware computers or gaming machines, you'd buy, I don't know, 1 kilowatt power supply. It'd be like this big with all these cooling tubes and stuff like that. They're not operating at frequency. He's trying to push the limits and operate at megahertz type frequencies, right? So then he's going to be able to use capacitors. He's going to be able to use actually the printed circuit board as a capacitor. He can be able to use the printed circuit board as an inductor. Just draw some wires in the printed circuit board, and it will be an inductor. Right? He just needs a small value of inductance. Right? He doesn't even need a core. He can use an air cored inductor, or maybe sandwich. In a printed circuit boards are multiple layers. Maybe sandwich a core material within 2 layers of a circuit board and make an inductor that way. Right? He can live with stuff like that because he's pushing the frequency limits. Right? So, but when you're operating at very low frequencies, like typically for these simple power rectifiers, of course, it doesn't. I mean, you're going to be using when you calculate in your homework, you will calculate hundreds or thousands of microfarads. For him, he wants to use picofarads and nanofarads and stuff like that in the same power rating for a converter, right? He can do that because of the switching frequency, and I hope it's clear. Is it clear now how the L's and C's will differ? Okay, so at least I want to wrap this up, and we spent the whole class on this. So just now the equations that govern this, okay? So now we know that this exponential meets the sine wave at this point, right? The book calls it, pi plus alpha, or alpha angle after pi, okay? So this is a point pi plus alpha. And we know that the capacitor voltage and the input voltage, they sort of separate, a little bit beyond the peak at some angle theta, beyond pi over 2, right? So if I would like to exactly calculate my ripple, it's the difference between my maximum value and my minimum value, which in this case is this point, right? So my maximum value and the minimum value, right? So the equation for that is this, right? So I have a delta V is equal to V maximum minus the absolute value of my sine wave, because I don't have the negative portion because of the full wave rectifier, has flipped the sine wave, right? So it's the absolute value of V maximum sine pi plus alpha. So this is the V maximum sine pi plus alpha at this point, right? So this is my minimum. Right? I'm subtracting my maximum, V maximum, minus my minimum. My minimum is, the V maximum sine, what? Pi plus alpha, which is the value of the sine wave at this point, right? So this is the exact equation, right? You can calculate using the exact equation, no problem. But to calculate using the exact equation, we go back to the same thing we had last chapter. We need alpha here, right? I need alpha. So how do I find alpha? Alpha can be found from what? This intersection with this waveform, so the intersection of this exponential waveform, ae to the minus t over tau, the intersection of this exponential with my sine wave happens at some point alpha. So how about I use that? So what they do is they equate these two equations. They equate, the Vmax, the ae to the minus t over tau, ae to the minus t over tau at a point omega t equal to pi plus alpha. So they replaced omega t with pi plus alpha. So at this point, the exponential is equal to my sine wave. So they replaced omega t with pi plus alpha, and they equated this with V maximum sine omega t, but they flipped. Instead of using the absolute value, they put a minus sign instead of, so it's like, flipping the sine wave. So it's minus V maximum at where? At pi plus alpha. So they equated these two. They equated these two and tried to find, the objective was trying to find alpha, right? But they ended up with an equation that had theta, right? The same mess that we had last chapter. They ended up with an equation that has theta. That cannot be solved with a closed form solution. That needs your calculator to solve, right? So, but before even using my calculator to solve for alpha, I need to find theta. So how do I find theta? Theta is the point where these two slopes for the capacitor voltage, which is the exponential equation, and the slope of my sine wave, at that point, these two slopes are equal. So what they did was differentiate the value, the sine wave, and differentiate my exponential and equate them. I don't show the equations here. I don't want you to memorize the equations. You need to understand the process here. So they differentiated both equations and they equated them to find theta. So they were able to find theta. You can now take theta, plug it into this equation for that you have alpha and theta in, and use your calculators to solve. And that's for you to find an exact solution. This is what you would use if the time constant that is required, for example, if I tell you that the RC time constant is large, or 3-4 cycles, right? I think the homework they give you, they tell you the time constant of the RC circuit is large, like 3 tau, 4 tau, or whatever, right? For large time constants, they have an approximation, right? For large time constant, for time constants for the RC circuit that are very low, meaning there will be a significant delta V. For a significant delta V, meaning this theta is pretty far away, meaning that this point is going to fall down considerably, you cannot use the approximation. But for small values of delta V, meaning you've properly chosen your capacitor to maintain minimum ripple, then you can use this approximation. Right? So does everybody see the difference between this delta V equation, this delta V equation? This is exact. You're more than welcome to use it. Or if in the homework they tell you that the time constant of the RC circuit was chosen such that ripple is only 5%, ripple is only 10%, or the time constant of the RC circuit is like 5 tau, 10 tau, large, then the capacitor will not discharge except after 10 time constant, 20 time constant. It's fine. Then you can use the approximation because delta V is small. The derivation for the approximation, I don't want you to know. I mean, you can look at. I think you should look at it just from a engineering perspective. It's good to see what's happening and what approximations they use. But at the end of the day, this is the equation that you will have in your homework sheet, and you can use it when delta V is small. Delta V is large. You have to use this large equation. Okay. So hopefully this covers the question on the quiz and this slide.
Okay. That didn't help for the piece by you said we were going to go over.
Yeah, so we'll try to. I don't think we're gonna get to the three-phase. We'll just cover the voltage doublers and then we'll stop.
So cancel that portion of that halfway.
No, we'll just delay it until we cover the three-phase rectifiers. So we covered. Let's first finish this and we'll discuss that. So we've covered basically most of the rectifier circuits, the classical rectifier circuits. Sometimes there are some special cases. I want to convert from AC to DC, but I want to double my voltage. Like here, my input voltage is this waveform, right? This AC voltage wave. My output voltage, its peak value is going to be equal to my input, right? Its peak value is equal to my input. But what if I want my output voltage to be double my input? Or what if I want and I don't want to use a transformer? I can use a transformer. I can put a transformer after here, and I put 1 to 2, a step-up transformer, and I can get double this. I can do that. But there are, some, people come up with other circuits. So these are two circuits that one would give you output voltage double the input, and one would give you the option of it being equal to the input, so it's like a classical full-wave rectifier, or double the input. So how do these circuits work? Let's look at them quickly, and then we'll hopefully finish them here. So first, let's look at the top circuit. So as you see here, I have two capacitors. Okay, if these two let's say this capacitor. So these capacitors. If I am able to charge these two capacitors to my maximum voltage, V maximum, then I'm able to get 2 V maximum at the output, right? If I'm able to do that, then it's great. So how would I do that? So let's see what they're doing here. This is an AC source. Let's assume we're in the positive half cycle. If we're in the positive half cycle, this AC source, the most positive potential is here. The most negative potential is here. So what's going to happen? Will diode 1 conduct or diode 2 conduct? Huh? 1 will conduct. I'm placing the most positive voltage here, the most negative voltage here, and then beyond that, after this diode, I have a circuit that can draw current as soon as voltage is placed across it. So I have the condition for forward current, and then I've put the diode in a condition in the forward biasing condition from a voltage perspective as well. So diode 1 will conduct in the positive half cycle. What is it going to do? It's going to charge up this capacitor as well as what? Current will flow through here, back to this capacitor, back to the source, and this load is also connected, right? There's a circuit here connected as well, but current cannot go back from here initially. It cannot go back from here at all. It can go back from here, and what this will do is actually what? Discharge this capacitor, which was already, initially it's discharged, but let's say it will discharge this capacitor as well. So maybe this capacitor voltage will go negative, not positive. Right? It's going to push current in a different direction, this capacitor. Right? So some capacitors are bipolar devices, some of them. Electrolytic capacitors are not. Some capacitors are bipolar devices. Some capacitors are not. If you put a negative voltage across it, it will blow up. It's the construction of the capacitor. I put some videos about the different capacitor technology. It's good that they brought that up. So there are some videos here. It's a really funny guy. He discusses, 10 minutes. But he discusses the different types of capacitors. It's a nice, 10-minute videos just for knowledge, okay? So it will not affect your circuit understanding here. So now current will go and charge this, the voltage, the supply will come in and charge this capacitor. And again, like my previous cases, if I've properly chosen my size of the bucket, right, then the capacitor will maintain the voltage to a large extent, right? But what's going to happen beyond the peak value of the sine wave? Same thing that we had before. During the first half cycle, beyond the peak value, this capacitor voltage, let's say, is maintained, and I have a small current being drawn here. So this capacitor voltage will be higher than the source voltage. Same thing as the rectifier. And this diode will stop conducting. Right beyond the V peak. Right beyond the V peak, the same story we had before. Right beyond the V peak, capacitor voltage will be maintained, supply voltage is going down. I've blocked D1 from conducting. But I've maintained the voltage across this capacitor. So if this capacitor has some voltage, this capacitor has some voltage, and then there's a load across them, then I'm actually feeding my load. Right? Let's say this is now my diode has disconnected. I'm still in the positive half cycle, my diode has disconnected, but I've charged this capacitor to V maximum. And this capacitor, fine, let's say is discharged or zero. Fine, has 0 volts. But if you look at this loop, I have a voltage source that is connected to my resistor through a closed loop. right? So I'm able to supply my load. If the load is drawing too much current, again, that means I didn't properly choose my bucket size, my capacitor size. So same as the rectifier, same as the previous rectifier. That's in the positive half cycle, right? So I'm charging the capacitor, and then same thing, disconnecting my diode. And as soon as I disconnect my diode, the only thing that can feed my load is my capacitor through this loop. Okay? Negative half cycle, what's happening? In negative half cycle, this is flipped in polarity, right? So I'm putting my positive voltage here, my highest potential here, my lowest potential here. So this is the lowest potential in the circuit, and then this is a higher potential, right? So what will happen? Diode D2 can start conducting. So if D2 starts conducting, it will push current in the capacitor in this direction, charge C2. So current will flow from here, charge C2, back to my source. Charge C2, back to my source. Right? So now what did I do? I've charged C1 and I've charged C2. Right? So I've charged C1 and C2, each to V maximum. Right? Assuming that I was able to properly choose C1 and C2 so that they are quite large compared to the amount of water that the load is taking out of them, then C1 and C2 will be able to maintain the voltage. And now these two are charged and they will be feeding when this is not being charged. When this is not being charged, it's feeding the load. When this is not being charged, it's feeding the load. Otherwise, it's being charged by the supply. And the supply is feeding it and giving a little bit of current to the load as well. Okay? So does this look okay? So how does the output voltage look like? Output voltage in the first half cycle, this capacitor is charging. And what's happening during this capacitor, when this capacitor is charging, this diode is off. If this diode is on, if diode D1 is on and it's charging C1, what's D2 doing? D2 is off in the first half cycle. If D2 is off, and this capacitor was charged before, but now it's only supplying the current. So you will have one being charged, one being discharged, one being charged, one being discharged, one being charged, one being discharged. But if you properly chose their values, then they will both be close to Vmax, and when you add them, your output will be close to 2 Vmax. But you will always see some ripple. One is being discharged, the other is jump and be charged. One is being discharged, and the other will jump and be charged here. So this is the input voltage here, and then these are the individual capacitor voltage, the green and the pink. Okay, so one is being charged. Initially, fine, forget it. Initially, the other is not being discharged. But here, one is being charged. Let me zoom in. If you see here, the green, for example, is going to be charged here at this point. Right? And then, during this time, what was happening? The pink was charged here. There's a jump here in the pink. And then it keeps discharging until here. And the pink charges again. And then this charges all the way until here. In the middle, the green charges up. Right? So in the positive half cycle, the green is charging. The negative half cycle, the pink is charging. I don't know, maybe it's not very clear. Pink is charging here, the green charges in the positive half cycle. Pink is charging in one, okay? So they do this, they alternate. So the output voltage, you will see one being charged, the green being charged, here the pink being charged. Green being charged, pink being charged. Alternatively, right? But if you draw too much current, all of this will collapse. Simulate it and keep decreasing the value of resistance, and you will see all of this collapse. That makes sense, right? It's going to collapse. You will not be able to charge one. One will not. If you're not able to charge one, then you try to charge the other, and then by the time you try to charge the top one again, the bottom one is discharged, and you will never be able to maintain the output voltage at all, right? So this is one doubler circuit. This operates exactly the same way, except that I'm able to, if I open up the switch, or we can do it next time, but when the switch is open, it operates like a full wave rectifier. Simple full wave, right? Just a simple full wave rectifier like we just covered. When the switch is closed, what's going to happen? When the switch is closed, in the positive half cycle, I do the same thing that the previous circuit was doing. Through diode D1, I'm charging capacitor 1, and current is flowing back to my source. And the negative half cycle, I'm doing what? Current is going through D3 and going back. In the negative half cycle, in the negative half cycle, I'm charging C2. I'm charging C2, and current goes back through D4, right? So initially, current goes through D1, right? In the positive half cycle, charges my capacitor, also feeds the load, right? And then current goes back through my supply terminal because I've closed the switch. Negative half cycle. Current flows out of this terminal, charges C2, and then goes back through D4. Right? So the function is exactly the same as the previous circuit here. Just that this one has the additional functionality of being able to charge to Vmax at the output or 2 Vmax, right? But if you look at the waveform, one is charging, the other charges in the other half cycle. So try to go through this one as well. Yeah. So that we'll stop here. Next time we'll continue and get to the labs issue.